This is project 3 for Fundamentals of Aerodynamics using Fluent 2D flow simulation of Combined Poiseuille and Couette flow. My partner is Garen Lamb. In his YouTube video, he has shown the setup of the Ansys Fluent as well as showing parts A through C. So I will be going through parts D and E. So to start, we can look at D, which is determine the maximum velocity and the height at which maximum velocity occurs using our Fluent results. So if we go over here in our report, I have in part D the max velocity of 7.441 meters per second at a height of 0.0588 meters. And in Fluent, I'll just go to Fluent right now. To determine this, you can come down here into reports. So it'll be down here in results and down to reports. Open that up. And then double click on surface integrals. You'll choose facet maximum, velocity, velocity magnitude, select all of these surfaces and click compute. And right here in our console, it shows our velocity is 7.4411898 meters per second. So I just rounded to 7.441 meters per second. And here I have the velocity profiles of the outlet and the midline, which in Garen's video he shows how to get that, but just to show you guys, I already have it here. We'll list it as the end plot. We have the mesh, y coordinate, velocity, velocity magnitude, x-axis, click end velocity. And then from here you can right click on the midline plot that we made and then press add to, and then add here. Now that we know our max velocity, from this graph you can obviously assume that the max velocity is here. So if we go ahead and zoom in, we can go to this point, which is where the max velocity is. And it gives us, it gives us our height of 5.88 times 10 to the negative 2, which would be 0.0588 meters. And that's how we got our max velocity and at what height it occurs. Going back to the project description, it asks us to determine the pressure gradient using the Fluent results with the theory. So here on the report, I have all my work, so we can run through it. It's asking to determine the pressure gradient, which is dP dx. In a previous lecture, we have determined that the velocity profile for a combined Poiseuille and Couette flow is equal to 1 over 2 mu, which is viscosity, times dP dx y squared plus first constant y plus second constant. Here I just noted that our viscosity used was 0.32, which is obviously shown in Garen's first video. From here, we know that if our y equals 0, which is where our bottom plate is, that our velocity will be the bottom plate velocity, which is equal to negative 2. We get that from the project description right here, moving plate velocity of negative 2 meters per second. Plugging in y into this velocity profile will leave us with C2. That will be, so C2 will equal negative 2. Now if we set y equal to h and plug that in, we'll be left with this. Here plugged in viscosity, plugged in h at each y, plugged in our constant 2 that we found, and this will all be equal to 3. As we see here, the moving top plate velocity is 3 meters per second. So all equal to 3, h is 0.1 meters. That was the h that we had set for our project. So we plug in all those values, 3 equals 1 over 0.64 dp dx, plug in our h value, 0.1 squared, plus c1, 0.1 minus 2. We add 2 to this side, take out 0.1 or factor out 0.1, and then from here we can solve for c1, and we get c1 is equal to 50 minus 0.15625 dp dx. Plugging in our new c2 value and c1 value into this velocity profile form, then we are left with our velocity profile equaling 1.5625 dp dx y squared plus 50 minus 0.15625 dp dx, all multiplied by y, minus 2. From here, we know the formula for our average velocity, which is the integral of the velocity profile from 0 to h divided by the height. We also know that our average velocity is 5 meters per second. We get that from here, our free stream incoming velocity, and it's steady flow, so our average velocity will be 5 meters per second. So plugging in this velocity profile into here, taking the interval from 0 to h, we are left with 1.5625 over 3 times dp dx h cubed plus 50 minus 0.15625 dp dx times h squared over 2 minus 2h, all divided by h, and we can set this equal to 5 because we know that our average velocity is 5. Now dividing each of these terms by h, we're left with 5 equals 1.5625 over 3 dp dx h squared plus 50 minus 0.15625 dp dx multiplied by h over 2 minus 2. And from here we can plug in our h, which is 0.1 meters. Adding 2 to this side, we have 7 equals 0.0052083 dp dx plus 2.5 minus 0.0078125 dp dx. We subtract 2.5 to this side, and then we can combine these like terms. 4.5 equals negative 0.0026042 dp dx. From here, you can divide 4.5 by this value here, and we're left with dp dx, our pressure gradient, equals negative 1,728 pascals per meter. Now, if we wanted to compare this to what value we get directly from Fluent, we know that our pressure gradient would be the pressure at the outlet minus pressure at the midpoint divided by length. Because we're doing outlet to midpoint and not outlet to inlet, we'll use 7.5, which is half of the 15 meters that we set our length to. To find pressure outlet and pressure midpoint, you can go back into Fluent, go into reports, click on surface integrals. You'll click area weighted average, change this field variable to pressure, leave it as static pressure, and we're going to compute from end velocity and midline. So we get our outlet pressure to be negative 53.622212 pascals, and our midline pressure to be 12591.704 pascals. So coming back into here, I plug that in, divided by the length, which is 7.5, and we get negative 1,686.04 pascals per meter, which is pretty close to this value here. So it ended up giving us a percent error of 2.49%. And that answers part D and E. And that concludes part 2 for project 3, Fluent 2D Flow Simulation of Combined Poiseuille and Couette Flow. Thank you.